Start the clock. Hello everyone, my name is Richard Murray from ORCA Computing, and we're building photonic quantum computers that we hope will be useful for machine learning. So here's a bit about the team. We're a bunch of very, very talented research people mostly from the University of Oxford, spun out from Professor Ian Walmsley's lab at Oxford. But I think quite exciting for me recently has been being able to attract some pretty significant leaders from the HPC world, mostly Per Nyberg, who's in the crowd today, and Mike Pereno. So with this nice sort of coming together of great technical expertise and business and delivery expertise. So maybe to start off pretty provocatively, we believe that quantum computers should look completely different from how most people imagine them to look. So our systems predominantly, as much as we can, cryo-free, in a rack, easily integratable within a data center infrastructure, and at a price point that is different from what people expect. So you don't see multiple millions of dollars for a system from us. We're aiming for our systems to be in this price point of less than $1 million and all of the advantages that brings. How do we achieve that? So this is the only technical slide I have. When you're working with single photons to build them into quantum computers, one of the most important things that you need is control of those single photons. Photons defy being controlled, and ORCA has 3 technologies which really help with that, giving us the ability to control single photons across the time domain, so being able to control the timing of single photons with controlling their frequency and controlling their switching. And it's the coming together of this control over those 3 different domains that allows us to scale up quantum computing in the way that we believe is important. So one major attribute of ORCA system, you've heard the fact that we believe in sub-$1 million price points, is being able to reuse telecoms components to build quantum computers. So we do not believe in doing a lot of stuff ourselves. We believe in leveraging what's already out there, existing optical fiber, optical switches, and other devices you can buy off the shelf and are used in the telecoms industry. We believe in repurposing those for quantum computing. And therein, we believe, lies some of the major commercial applications of quantum in the short term. So when you talk about short-term applications of quantum, people look at you a bit funny. NISQ applications of quantum is an unproven area. We believe there's a lot of excitement, a lot of reason for believing that NISQ systems, in particular photonic NISQ systems, are potentially useful, are exciting at least. And our team, predominantly working in machine learning, have identified a few areas where that might be true. So let me be clear here, we're applying a non-universal quantum computer to some very cutting-edge applications in machine learning. And we see some areas of optimization, of generative modeling and image classification that are starting to show us a roadmap towards those being exciting. And that's the thing that everyone is looking for in the industry, those short-term applications. We published a few cool papers. So we've shown for the first time the application of boson sampling, photonic boson sampling systems to the QUBO problem, an optimization type problem, previously thought only possible with D-Wave machines. And we've shown some interesting work in applying photonic systems to what are known as latent spaces, which are inputs into generative models for AI. So my last slide, just to really try and convince you about quantum machine learning. I know there's a lot of skepticism, a lot of maybe useful belief that it won't happen. Why do we believe? We believe because non-useful quantum advantage has been demonstrated. There is a device on AWS you can access today that has quantum advantage in a non-useful way. But we see the first signs of mapping not useful onto useful through machine learning. By useful, we mean some valid improvements, and by the way, we don't just mean supremacy, we mean more useful and genuinely commercially useful. But of course, we also mean applications that are scalable, that are real world, not toy problems, and have some advantage for these non-universal photonics machines. And I will just say as a final thing about how we do that, that's only possible if you really know what you're looking for. So our team really understand machine learning, and therefore they know what's interesting in machine learning but not useful, and therefore how quantum computers can really affect the short-term prospects of quantum machine learning. And I think that's it. There's the team. Thank you very much.